right, so far we've looked at a particular example. Now let's just take any function in general. Okay. We've got a function here and say we dictate an epsilon equal to 1 over 10. And here we see that the limit of the function as x approaches x sub 0 is equal to L. And again, if we created this horizontal road strip with width equal to twice of 1 over 10 right there, then the thing that we need to find out is what happens in the x's, how close should the x's be so that this y values remain in the horizontal strip. So we want this to be true, right? So our response is we need to find a delta which is a symmetric interval about x sub 0 of width twice delta, of course, because this is delta and this is delta. And you notice that as long as this is true, all right, this is what this means. It's the same as we're saying the x's are within this interval, then we can guarantee that this inequality will hold, because look at all these y values. These y values are all contained or within, are all sitting inside the horizontal strip. Okay, now let's say we make our epsilon equal to 1 over 100. Then again we create a new horizontal strip centered around our limit value L. Okay, and again we want this to be true, but now for what values of x's, or how close should x's be? So we want this to be true, but our question is how close should the x's be around x sub 0. So again we will find a delta, so we go and project down and find an interval that contains x sub 0. So here's the interval that contains x sub 0, and then we get a delta, which is a symmetric strip of width 2 delta, right? So if we stay within this area, then we know that its corresponding y values right here would stay within the yellow horizontal strip, which means these y values satisfy this inequality. Now let's get an even smaller epsilon. Epsilon equal to 1 over 1000. So in this case, we created this time a smaller width of a horizontal strip that is centered at L. Okay, and that's our new challenge, and we want to make sure that f of x minus L is less than 1 over 1000. Will we be able to find a delta, right? Well, I'm sure we'd be able to find a delta as long as we get this interval that contains x sub 0. So there's your interval. And then we find a symmetric blue strip right here of width twice delta, delta to the right and delta width of delta here and delta to the left of x sub 0. Okay? And there it is. So that if this is true, then we are guaranteed that the y values remain within the horizontal yellow strip. And we can keep going as much as we can. And again, let's say our epsilon is even much smaller. Okay? So our epsilon is 1 over 100,000. Again, we'll find another delta right there that depends on our epsilon. Okay, so that if our x's remain within this twice delta strip, then we know that the y values will all be contained in this small bandwidth, this small horizontal yellow strip. So we see that from all these slides that I've shown you with different values of epsilon, that delta depends on the given epsilon. Okay, so you're given an epsilon, and our goal now is to find a delta so that for all x's within this interval, we are guaranteed that the y values remain in this interval as well. Okay, so how do we find a delta algebraically given the function? Given f, of course, its limit at as x approaches, say, x of 0 and an epsilon greater than 0. So the process of finding a delta involves two steps. First, you solve the inequality like we started in the example that I gave you. So we've solved the inequality of f of x minus L less than epsilon. We will find an open interval that will contain x of 0. And then from there, we will be able to find a value of delta so that this open interval centered at x of 0 will be contained in the interval AB, which we got from step 1. If we find that delta, then this inequality will hold for all x's in that delta interval. Okay, let's go ahead and pick out an example. So example 2, you can refer to your ebook on page 61. Show that the limit of 5x minus 3 as x approaches 1 is equal to 2. Okay, so what is given here? We're given that x of 0 is equal to 1. F of x is 5x minus 3, and of course the limit is equal to 2. Now here we did not specify an epsilon, so we're just given epsilon greater than 0. So our goal is to find delta so that if, say, even if x is not equal to 1 and x is within delta distance around 1, that is, whenever x minus 1 is less than delta, then f of x will be, that means the y values differing from 2 would be less than epsilon. Okay, so our concern is we're given this epsilon right here. We find out what would be the delta so that, okay, that's what our delta is going to look like, or how long is this? So where did we get this epsilon over 5? Let's find out. Okay, it says in the first step is to solve this inequality. So what we have now is, let's go ahead, okay, so to find the delta, we have to work backwards from the epsilon inequality. So we solve first, solve 5x minus 3 minus 2. See, this is now your f of x minus L less than epsilon. So if we do that, what we'll get is 5x minus 5, okay, is less than epsilon, which is equivalent to solving the inequality. 5x minus 5 is between minus epsilon and epsilon. Okay, so now we add 5 everywhere. So 5x is now between 5 minus epsilon and 5 plus epsilon. And then lastly, we divide everything by 5. Okay, and from here, we will see that x is between 1 plus epsilon over 5 and 1 minus epsilon over 5. And if we write this in interval notation, this would just mean that it's 1 minus epsilon over 5 and 1 plus epsilon over 5. Okay, so go back to the previous slide. Did you see now that this is the interval that we're looking at? 1 minus epsilon over 5 up to 1 plus epsilon over 5. Okay, let's continue our problem. From step 1, we found that the open interval of 1 minus epsilon over 5 up to 1 plus epsilon over 5 contains x of 0 equal to 1. From solving the epsilon inequality, f of x minus the limit L, which is 2, is less than epsilon. Now we find delta. And remember, delta must satisfy x minus 1 less than delta. So we need to find a delta such that this is true. So if we rewrite this, this means that x minus 1 is between negative delta and delta. So adding 1 to all throughout, we get that 1 minus delta is less than x is less than 1 plus delta. Okay, so look at this. If we take this inequality, that's equal to x is between 1 minus epsilon over 5 and 1 plus epsilon over 5. So naturally, what do you think should be our choice of delta here? In order for this to match, then we choose delta to be just equal to epsilon over 5. So that if we choose this, then for all x's such that this is true, then f of x minus 2 is less than epsilon. So we have already shown that if we choose delta equal to epsilon over 5, then this inequality holds. If this inequality holds, then we are guaranteed that the f of x's differ from 2 by less than epsilon. Now, remember our choice of delta is equal to epsilon over 5. Can we choose a smaller delta? Of course. As long as it's less than or equal to epsilon over 5, this inequality will still hold.